Okay, so unit number 4 is related to the binary search tree. So binary search tree is also known as ordered binary tree. So ordered binary tree. So ordered binary tree means what? The tree in which each and every node is in the order fashion. Okay, so here inside the binary search tree, all the nodes, suppose this is the root element, then whatever the nodes which are available in the left are less than root, and whatever the elements which are available in the right are greater than root node. Okay, so here you might consider this particular case. So this is the root element. So whatever the contents which are occurred inside this particular left part that are less than the particular root element, and these are the particular content that are greater than the particular root element. Okay, so all the nodes in the left subtree have the values which are less than the root node, and all the nodes which are in the right subtree having the value either equal to or greater than the root node. Okay, so this is the simple logic related to the binary search tree. So whenever any root element is there, whatever the nodes which are occurred at the left side that are less than the root node, whatever the elements which are occurred at the right side that are less than or equal to the root node. Okay, so same thing that are applicable to the subnodes also. So whatever the elements which are left to the 27 are less than 27, and right to the 27 is the greater than 27. Okay, so same logic that is applicable. So this is the example, simple example for the binary search tree. So here root is 39. So whatever the left subpart are includes the particular 9, 10, then 19, 18, 19, 21, 27. So these are the particular elements. Again 28, 29, 36. So these are the particular elements which are less than the 39. And these are the particular right subtree having the elements which are greater than the 39. Okay, so this is the simple logic which is used inside the binary search tree. Okay, so if uh, there are the trees in such a way that only left subpart left elements are there or only right elements are there, then this is called as left skew. Left skewed binary search tree, and this is called as right skewed binary search tree. That is all the elements at the left, all the elements at the right. Okay, so here some are the examples which are given related to check whether the particular elements are binary, whether the particular tree is binary search tree or not. Okay, so in this particular example, 21 is a root node, 22 is greater than 21, but it is the left side. So this is not binary search tree. Okay, again this particular example, all the nodes which are less, yes. So this is the binary search tree. So how to judge? Check the root. Whatever the left element must be less than of that particular element, and right element must be greater than that particular element. So again in this particular example, this is not the binary search tree. So these are the few examples related to the binary search tree. Okay. Now, suppose in exam there may be a question that create the binary tree from the given example. Okay. So in that particular case, how to create the binary tree? So first element you have to just treat as a root element. Okay. So just take that particular root element as like this. Then second element must be inserted at the left. Third element at the right. Then, so these particular two elements are gone. Again 12. So 12, just compare whether it is a left side or right side. So 40, if 45 is our root element, then 12 must be at the left side. So 12 is gone over here. Again check 34. So 34, it is again left side, but it is a part of this particular element. That is, so it is again less than 39, but greater than the 12. So it is inserted in the second level. Okay, as a child of 12. Then go to the 78. So 78, just check with the other elements. So it's the children of that 56. So 70 is attached as a children of that particular 78. Again, just check for 32. So inside this particular 32 must be placed as a left of this particular 34. Okay, so it is just placed over here. So I will just so new element is inserted. I just mark that new element. Then 34. Then 78 over here. 78. Again 32. 32 is attached over here. Again 10. So 10 must be at the left side of this particular 12. Again it goes to the 89. So 89 it is inserted over here. After that we are having 67 and 80, 54, 67 and 81. So 54 is just check for this particular. So where 54 is fitting, it is greater than 45 but less than 56. So that's why it is inserted at this particular location. Again 67 and again 81. So in this way, the binary search tree has been created from the simple example. So this is the simple example where we can able to just create or just insert the particular nodes one by one. So you can manually take any example and you can just draw the binary search tree inside that particular example. Then here there are the different operations related to the binary search tree. So it just start with the searching, then inserting new nodes and deleting the nodes from the binary search tree. So whenever we are just searching the particular data, then what is our requirement? We have to just start with root element. Okay. So if number is less than root element, then search inside the left part. If number is greater than the root element, search in the right part. Okay. So same logic that is given over here. Suppose I want to just find the particular node of value 67. So 67 just compare with 45. So it is greater than this particular 45. So just search inside the 56. Again, it is greater than 56. So it will just go inside this particular. So again, compare with the 67. It must be the left side of this particular 67, 78. So again, you have to just search over here. and this is the particular element which is found. So whole this particular algorithm that is given over here. So algorithm to search the given value. So if tree point to the data is equal to value, or if tree is equal to null, that is if whatever it just start with the root element. So if tree data is equal to value, then it just return that particular data. And if tree is empty, then it directly return the tree. If value is less than whatever the data, then it goes to the left part. Okay, so whatever the tree of left and value, we have to just again recall. If it is greater than, then you have to go to the right part and just value. And you have to just repeat the particular content one by one, so that this particular loop is repeated for up to we are just searching the particular data. Again, inserting a new node inside the binary search tree. Okay, so what is the algorithm? If tree is empty, so this is the particular condition for empty tree. That is, if tree don't have any particular content or elements or nodes within the particular tree. So in that particular case, you have to just assign the particular tree data is equal to value. Then tree left is equal to tree right is equal to null. So we have to just assign the only root element, and whatever the left and right part are null. If else if value is less than tree. So if value is less than tree, you have to just insert the particular to the left side and value. Else you have to insert to the right side and value. And you have to just repeat the continue the particular loop up to we are just finding the proper location for the insertion of the particular element. So this is the simple algorithm. So in such a way that we can write the pseudocode. So this is called as pseudocode. So inside the pseudocode, we are having the number of whatever the algorithm name, whatever the input and output parameters, and these are the particular number of steps in the form of the description as well as looping conditions. Okay. So this is the example. Suppose I want to just insert the 12 inside this particular. So I first check for the root element. Root is there. So we just check whether the value is less than or greater than root. It is less than. So I just go to the left part. Again check whether it is less than or greater than this 39, less than. So I can able to insert this particular 12 over here. Okay, so this is how we can able to just search the particular element inside the binary search tree. Again, next operation, that is deleting the particular element. So this is related to the insertion. This is related to the searching. The next part, that is deletion. Suppose I am deleting any particular node. So for example, suppose I want to delete the 78. So 78 located over here. So you can directly search for the root element, then go to the right, again go to the right, and just find the particular element and just delete it. So here it is deleted. So this particular edge is deleted, and we can just delete the particular element. Suppose if we want to just delete the particular element with node. For example, suppose I want to delete the particular node 54, but 54 having the right child, that is 55. So what do we want to do? We have to just find the right element. So starting with root element. So you have to just visit over here, again here, just check the value, that is it is less than 56. So go to the here. Again, just remove this particular element, and whatever the children that can be just substituted over here. Okay, so remove the element. and substitute child value. Okay, so whatever the 56, that can be just shifted to the 54 and we can get the value as 54. Okay, so this is in case of one child element. Okay, so this is the one child element. Again, if that particular element having the two childrens. So suppose I want to just delete the 56. Okay, so I want to just delete this particular 56. So it is having the left child, right child, and it is having the again subchildrens. So suppose I want to just delete that particular, then how to delete? First, I have to just find the particular element. So 45, then 56. So 56 is found. Then what I want to do? I have to just delete this. So whatever the successor of this particular 56, that can be just substituted. Okay, so whatever the 54 is substituted, no, because we don't want to just hamper this particular tree. So we have to just replace this particular 56 with right child. So 78 we have to just replace. So again, so this particular 78 we have just replacing. Okay. Then we have to just change. So whatever the successor value, we have to just replace over here. So 78 we have to just go over here. Again, this particular 80 we have to just shift it over here. So 78 is shifted in first phase, 80 is shifted in second phase, and whatever the duplicate element I have to just remove. So I can just handle the particular duplication. Okay, so whatever the right successor, we have to just okay, so here there are the given the rules, that is successor or predecessor. So you can just, if left part is there, you can use the predecessor, and if right part is there, you can use the successor. So this is the particular algorithmic steps related to the deletion. So if tree is empty, then you have to write the message that value is not found. If it is less than the value of root node, value of the particular to be deleted, then go to the particular left part. If it is greater than the particular whatever the root node, then you have to go to the right part. Else, if tree is left and tree is right, then you have to just find the temporary location, find the largest node name, and you have to just keep as a data and delete the left part. Similarly, for the right part and so on. Okay, so in this way, we can just use the deletion operations inside the binary search tree. So all these particular steps are given over here. If you read that particular steps, you can directly get the particular content. So same programs you can able to implement by using the C programming. So here C is used. You can use C, Python and so on. So any language you can able to use. So these are the three operations related to the binary search tree. So first one, that is searching the particular node. Second, inserting the particular node, and third, deleting the particular node. Then next part, that is optimal binary search tree. So optimal binary search tree means what? The search tree which have the optimal, that is minimum cost for searching the tree. Okay, so optimal binary search tree means what? The tree in which there is a minimum cost for searching any node in the particular tree. Okay, so how to find that particular OBST, that is optimal binary search tree. So here there is a technique given. So we have to just calculate the weight value and we have to just formulate that particular value. And this is the particular algorithm. So let's see the example first, then only you can able to understand that particular. So suppose I'm having this particular node. So these are the 4 nodes in my binary search tree. So 15, 16, 18 and 20. And we want to construct the optimal binary search tree. So optimal binary search tree means what? The search tree having minimum cost of searching the nodes. Okay. So in that particular scenario, inside this, we don't know which is the root element, which is the child elements and so on. So this particular tree we can able to calculate, draw by using n number of ways. Either we can use this particular first way or we can use this particular second way and so on. So there are n number of ways where we can put the 16 as a root element or 18 as a root element. Okay. So which fashion we want to just use? So for that we have to just given the frequency for each node. Okay, so frequency of each node is given in the problem itself and we have to just find which is the optimal search tree pattern, that is whether to follow this particular or whether to follow this particular. So first of all we have to calculate the BST, that is binary search tree. So based on the levels, these are the particular levels. Okay, so for 16 there is 1, for this 15 and 18 there is a 2 and these are the particular 3. Okay, and we have to just consider the frequency of each node. Okay, so these are the levels and this is the frequency. Okay, so we just consider this particular nodes one by one. So 15 is occurred. So here first just process this particular first node. So 16 is a root element, so its level is 1 and its frequency is 2, so 2 into 1. So this is for 16. Then this particular 4 into 2, this is for 15, that is left subtree. Then this is for 18 and this is for 20. So whatever the total sum is the 31. Okay, so the cost for just accessing the binary search tree is the 31 for this particular pattern. Let's see the cost for this particular, this second pattern of the tree. So if 18 is the root element, so 1, 2 and 3. So this is for 18, this is for 16, this is for 20 and this is for 15. Okay, so depending on, we are just considering the frequency as well as the level. So 6 into 1 means we have to just consider 18 frequencies. So 18 frequency is 6. It is to the level 1. So 6 into 1 plus for 16, 20 and 15. So whatever the cost is 28. So from that we can just find that this particular approach having the minimum cost. Okay, so here we can just find okay, so we just use the algorithm to find the OBST from all possible sets of the BSC. So now we have to, what we want to do? We have to just plot the 4x4 matrix. So this is the particular 4x4 matrix. And we have to just check it out. What is the cost to search the particular elements? Okay. So why we are taking 4x4? Because we are having the 4 nodes. 4 nodes. Which are those? 15, 16, 18 and 20. So that's why 4x4. So if there are the 5 nodes, then 5x5. There are the 6 nodes, 6x6 and so on. Okay. Then cost for accessing the 15 as a root node is 4 into 1. So whatever the frequency of 15 is 4 into, this is the level. This is the frequency. Okay, so frequency is given in the example itself. So we can get the 4. Similarly, for 16 as a root node, for 18 as a root node, for 20 as a root node, we are having this particular cost. Okay, so here we have just substituted all this particular as this particular values. Okay, so for this particular calculation, we have just inserted this particular value. Then next step, here we have inserted only one node at a time. And it is root node. Okay, so this is the particular calculation for only one node at a time. Now suppose I want to insert the 2 nodes at a time. So suppose I want to just insert the 14 and 16 at a one time. So I just calculate the value. So sum of the frequency of 2 nodes plus minimum of this particular, that is either 15 is a root node or 16 is a root node. So whichever minimum we have to just consider. So frequency of accessing the 2 nodes is 6. Okay, so we have to just take the sum of the frequency of accessing 2 nodes. So 4 plus 2 is 6 and whatever the minimum is. So if 1 is root node, that is if 15 is root and if 16 is root. So here we consider this particular 2 and whatever the 6 plus 2 we have to add over here is equal to 8 and whatever the 6 plus 4 is 10. So we have to just consider the minimum. So from this stage we just take the 8 where root is 1. So root is 1 means what? Root is serial 1, that is 15. Okay, so whole value we can just represent it as 81. So this is the particular value which is coming by using this particular calculation. Okay, so 8 का साल का है ना. Now next part, that is we have to just consider next two numbers. Okay, so first, second we have just consider. Now we have to consider the second and third, that is 16 and 18. Again we have to just calculate the particular values for this. So whatever the minimum is 10 for which node, that is node number 3 for 18. Okay, so this particular value we have to just insert in the particular matrix table and it is inserted over here. Okay, so this value is inserted. So why it is 3? Because it is a third node. Again, we have to just calculate the same for again considering the nodes 3 and 4. Okay, so these are the 3 and 4 nodes are there. So we have to just calculate the minimum. So minimum is 12 for third node. So we have to write 12 of 3, that is for node 18. So I just write 12 and 18. Okay. Now in this way, now I have just inserted the two elements at a time. Okay, so all these particular calculations are for two elements at a time. Now here 3 elements at a time. Three elements at a time. Okay, so here now consider the 3 elements. So let's see, we are having the scenario as 1, 2, 3 or 2, 3, 4. So these are the two scenarios. So let's see which is the minimum from these 3. So we just insert the first, second and third serial number nodes, that is 15, 16 and 18. So these are the particular calculations. So from that 20 is the minimum for the third node. So I just write 20 of 3, that is 20 for node 18. Okay, so I have just inserted that particular 20 over here. Okay, so here I have just inserted that. Again, let's check the another combination, that is 2, 3, 4. That is second, third, fourth element, and we have to just get the particular minimum is the this particular. So 16 for the third element. So here 16 is inserted. Okay, so here 16 for the third element is inserted. Again, suppose 4 elements are inserted at time. Inserted at a time. So which are 4? 1, 2, 3, 4. So all elements that are inserted at one time. So which is minimum? That is 11. So whatever the minimum is 26. So 26 for which node? That is third. So 26 for 18 as a root. Okay, so we just inserted this particular 26 over here. So from this, we observe that the minimum cost is 26. So this particular minimum cost is occurred, and it is for which node? So minimum cost for 4 nodes is 26. When this is for third, that is when serial number 3 is inserted, that is node 18. Okay, so from there it is decided that the 3 will be the serial number 3 is the root node, that is 18. Okay, so we just consider the 18 as a root node, and from that we can just calculate the optimal binary search tree. So this is the root node. So this is the root node. So 18 as a root node, and whatever the other, we can insert it at the left side or right side depending on its value. Okay, so 16 is less than 18, so it is left side. 20 is the greater than 18, so it is at the right side. Again 16 so here it is wrong, given wrong. Here 16 is there and here 15 is there. Okay, so in big book there are some printing mistakes are also there. Okay. Okay, so in this way we can able to just plot the particular elements. So this is related to the optimal binary search tree calculations. The next one, that is self-balancing binary search tree. So self-balancing binary search tree is also known as height balance binary search tree, where it will automatically attempts to keep its height. So height means what? Whatever the number of nodes which are occurred. Okay, so number of levels of the nodes from the root. So it will be as small as possible. So based on the height, it will just do the transformations and it will just self balance that particular tree. Okay, so this is unbalanced tree. So if it can be just converted into the balanced tree, self balanced tree, by just adjusting the particular height. Okay, so it just perform the left transitions as well as right transitions and it will just balancing the height. So this particular node is moved towards the root node. That is whatever the node, and left and right. Again, here it is 27. Okay. So 27, 23, then 18, then 54. Again, 69 is there, 63, again 72 and 65. So it will just reduce height. So this is called as self-balancing balanced search tree. So from unbalanced search tree, it will just balance the particular tree. So whenever we consider the self-balanced search tree, then it is having the two implementations. First one, that is the AVL tree, and second one, that is red black tree. So let's see what is meant by AVL tree. So AVL tree is a self-balanced binary tree which is invented by these three persons, G.M. Adelson, then Waleski, and E.M. Lades. Okay. So with the help of this particular name of these three authors, A, V, and L, it is called as AVL tree. Okay. So in AVL tree, height of the two subtree may differ by at most 1. So it may be -1, it may be 0 or 1. So whatever the difference between left subtree and right subtree, it must be a -1, 0 or 1. Okay, so due to this particular property, it is also known as height balance tree. So AVL tree is also called as height balance tree. So how to calculate this particular balance factor? Balance factor is calculated by using this particular formula. So balance factor is equal to height of left subtree minus height of right subtree. So if balance factor is 1, then it means that left tree is one level higher than the right subtree. So it is called as left heavy tree. If balance is 0, then height of left subtree equal to height of right subtree. And if it is -1, then left subtree is one level lower than the right subtree. Okay, so it is also called as right heavy tree. Okay, so let's see the example. Okay, so here we can just have the example. So how to this particular balance tree factors? So it may be -1, it may be 1, or it may be 0. So how to calculate these particular factors? So for nodes which don't have any particular childrens are having the value 0. Okay, so 18 having 0, 39 is having 0, 54 is having 0, and 72 is having 0. Again, so I will just write it. Node having no child or only two child at same level having the value as 0. Okay, so you can just consider this node having don't have any child, as well as the node having the same height. Okay, so this particular left also having same height, right also having same height, so it is having the 0. Then if left is 1 more than right, then it is having the weightage as 1. Okay, so this is 0. So again, this 27 having the left children only, so its weight is 1. If he don't have any particular right children, then its weight is 1. Again, this particular left is also 1, but right is 0. So 1 plus 0 is 1. Again, 1 plus 0 is 1. Okay, so whatever the balance factor is nothing but whatever the weightage of left plus weightage of right. Okay, so you can just consider over here another example. So whatever the leaf nodes are 0, so 0 plus 0 0. Again, this particular is left node, so it is having the weightage as 0. So it is only having the left subtree, so weightage is given to the 1. So if it is having the right subtree, weightage is -1. So whatever the 0 plus right subtree, that is -1. So it is having the -1. Again 0 plus -1, that is -1. Okay, so in this way we can just able to assign the particular weightages. So how to decide whether we have to write the -1 or 1 or anything else, depending on the height. Okay, so here it is having the right subtree, left subtree. So height is 1 minus 0, that is 1. So if you just consider here, 36. So 36, it has the left subtree height is 2. This one. And right subtree height is 1. Okay, so 36 having the left subtree height is 2. That is first one, second one. And right subtree is 1. So 2 minus 1, that is, it is having the particular constant as 1. So in this way, we can able to calculate the height. So height, we can able to calculate the height by using the formula, that is level of or height of left subtree minus height of plus height of the right subtree. Okay. So this is the particular balance formula. So this formula we have to read. So height of left subtree minus height of right subtree. Then only we have to give the particular balance factors for each and every node inside the tree by just using this particular formula. Okay. Then with the help of this AVL, we can able to just again define the operations. So searching, so inside the searching, again, we have to just use the same way as the binary search tree. That is, we have to just calculate the node, and depending on the node value, we have to just again modify the operations. Then for insertion, we are having some separate value, some separate mechanisms for inserting the new node. So inserting the new nodes, so while inserting new node, check balance factor value is -1, 0 or 1 only. So if it is increases or decreases, we have to just rebalance that particular tree. Okay, so for example, suppose I just insert the particular value as 7. So where is 7? Not 7, 71. Then in that particular case, this particular height is goes to the 2. But what is our condition? It must be -1, 1 or 0. So in that particular case, we require to perform either left rotation or right rotation or left right rotation and right left rotation. Okay, so LL means left subtree of left subtree. Right RR means right subtree of right subtree. LR means right subtree of left subtree, and RL means left subtree of right subtree. Okay, so here we have to just perform the LL rotation. So LL rotation means what? Suppose this is the particular tree. Suppose I am just inserting this particular new node inside the tree. Then what are the adjustment that can be just done? So here LL rotation includes, we have to just rotate the particular content in such a way that we have to just rotate the particular content in the left side. Okay, so suppose this is the initial condition. So this is the initial. Whenever any particular node is assigned, so new node is assigned over here at this particular location, then in that particular case, we are just having the imbalance condition. That is, the value goes to the 2. So in that particular scenario, we have to apply the left rotation. So first, we have to just shift this particular element to this particular location, then shift this to here, and whatever the particular new node which is attached, that is just coming over here, and whatever the T1 and T2, this particular T1 and T2, that can be just go over here. So in this way, we can just apply the rotation. So let's see the example. So suppose this is the particular example. Okay. So I want to just insert the 18. So whenever I just insert the 18, it will go over here and just insert the 18. Okay. So in that particular case, this balance is just 2. So it is not valid. So we have to just apply the LL rotation. Okay. So inside this particular LL rotation, we have to just rotate the particular tree in this particular direction. Okay, so whatever the root node, that can be just rotated over here. Whatever the children's, so this particular node is coming over here, so it is the right, and whatever the 39 is left, and we have to just shift this particular 27 to this particular node. So 36 to the 45 and 27 and 18. So in this particular way, it will just balance the particular height. The balance factor is 0. So again, some mistakes are there in the book. So we can able to just correct that particular mistakes and go forward.
Balance is 110.
Yes.
36 1 येणार ना.
नाही. आता हे कशावरून डिसाइड होत आहे की आता तुमची लेफ्ट हाईट मायनस राईट हाईट. आता लेफ्ट हाईट किती आहे आपली 1 2. राईट हाईट किती आहे 1 2. So 2 minus 2, that is 0.
ओके.
आता ह्या एक्झाम्पलचं बघा, आता सिंपल एक्झाम्पल, आता इथं आपल्याला कळत नाही, हे पहिले एक्झाम्पल बघा इथं. आता इथं 27, आता 27 ला काहीच नाही, लेफ्ट पण नाही राईट पण नाही. सो हाईट इज 0 minus 0, दॅट इज 0. आता इथं आलं, त्याला किती आहे, तर लेफ्टची हाईट 1 आहे, राईटची हाईट 1 आहे. So 1 minus 1 is equal to 0. आता ह्या नोडला लेफ्ट आणि राईट काहीच नाही, सो इज इक्वल टू 0. आता इथं बघा 45 ला, आता इथं हाईट किती आहे 1 आणि 2 मायनस, आता ह्याची राईटची हाईट किती आहे तर 1, सो इट इज 1 यायला पाहिजे इथं, तर -1 नाही 1 यायला पाहिजे. ओके, सो लेफ्ट हाईट ऑफ लेफ्ट सबट्री मायनस हाईट ऑफ राईट सबट्री, जो आपला इथं फॉर्म्युला आहे, सेम फॉर्म्युला वी हॅव टू रेफर. ओके, सो हाईट ऑफ लेफ्ट सबट्री बॅलन्स फॅक्टर कशावरून कॅल्क्युलेट करतोय, तर आपण या पर्टिक्युलर फॉर्म्युलावरून कॅल्क्युलेट करतोय. सो हाईट ऑफ लेफ्ट सबट्री मायनस हाईट ऑफ राईट सबट्री. सो काय काय वेळेला आपल्या बुक मध्ये चुका आहेत, कारण जेव्हा एडिटिंग होतंय तेव्हा हे मायनर चुका बहुतेक लक्ष दिलं नाही, त्यामुळे बुक मध्ये चुका आहेत काय काय वेळेला. So we have to just correct it and we have to just solve the programs. आता ह्या सबट्रीच इथलं एक्झाम्पल बघा, आता ह्याची हाईट किती आहे लेफ्ट सबट्रीची 1 2 3, सो 3 मायनस ह्याची किती आहे 1 आहे, सो बॅलन्स फॅक्टर इज 2. Okay, so in this way there are just few mistakes are there. So in that particular scenario we have to just correct it and we have to follow that. So these are the particular LL rotation. Again RR rotation. So RR means what? We have to just shift all this particular in the right side direction. Okay. So this is the particular example. So again, this particular example. So if new node is inserted, so if 89 is inserted, then balance factor is just change. So we have to take care that balance factor must be either 0, 1 or minus 1. So we have to apply the right rotations. Okay, so whatever the 45, we have to just move towards here. So here I just apply this particular. And whatever the other nodes, it will just shift it over here. So whatever the height is 2 minus 2, that is 0. Again here 0 minus 1, that is minus 1. Again here 0 minus 0 is equal to 0. Here 0 minus 0 is equal to 0. 0 minus 0 is equal to 0. Again 1 minus 1 is equal to 0. And here this is the particular height. So this is related to the right rotation. So that's why I just show the arrow. Then LR and RL. So LR means first left shift and then right shift. So suppose 37 is inserted. So in that particular scenario, we have to apply the right shift for the left subtree. Okay, so here this particular element is moved towards here. This particular element is moving at the root element and this particular to the left. So here and for here we just apply the right. Okay, so that's why it is called as LR. Okay, so you might consider a new node is inserted in the right subtree of the left subtree of the critical node. So LR कधी अप्लाय करायचं तर न्यू नोड जर राईट सबट्रीला इन्सर्ट केला ऑफ लेफ्ट सबट्री म्हणजे लेफ्ट पार्टच्या राईट सबट्रीला आपण इन्सर्ट केला तर LR येणार. Okay, so here लेफ्ट सबट्रीच्या राईट सबट्रीच्या लेफ्ट पार्टला जर इन्सर्ट केला तर LR येणार आणि जर इकडच्या बाजूला इन्सर्ट केला तर RL येणार. ओके, so it will just apply the particular LR operations and here the RL is used. That is if new node is inserted at the example RL. So this is the right subtree where we can just insert it at the left part. Okay, so it is called as RL. So in this way, we can just have the particular operations, and by just using this particular operations, we have to just construct the particular tree. So whenever you are just going through the description of this particular whole problems, you can able to understand how it will just exactly work. Okay. So our task is just to balance this particular factors. So it may be -1, 1 or 0. So if it is greater than -1 or greater than 1, then we have to just adjust this particular factor by using the LL or RR or LR or RL algorithms. Then same way, we can able to delete the particular contents. So these are the particular deletion operations. So same way, we can able to apply the deletion So if one node is deleted, then what happens? So suppose here 72 is deleted. So 72 is deleted, then in that particular case, this particular balance is just unbalanced. So it is more than 1. So we have to just perform the particular left shift. So we have to rotate in this particular direction, and this 45 is shifted to 40 here, and it will just readjust the particular element so that the right rotation that can be just happen. Similarly, double right rotations that can be just happen. So these are the particular three that are given over here. So suppose 72 is deleted. So in that particular case, what happened? This is unbalanced. So first of all, we have to just right rotate, and again here we can also apply the right rotate so that we can able to perform the R1 rotation. So all these particular formulas and all these particular adjustments related to this that are given in each and every example. So our task is just to go through the description and whether check whether it is correct or not. So this is the particular example which is given for each and every rotation. So you can just go through these particular examples and just check whether the particular node is deleting or not. So you can manually choose any particular node and try to just apply the AVL algorithms as well as rotations and check whether the balance factor is 1 or -1 or 0. If it is not, then apply the rotations. Okay, so this is the only logic that can be just used inside the AVL tree. So again, it is a code related to the AVL tree implementation. Then the last part in our unit is the red-black tree. So again, it is a one part or one type of the self-balancing binary search tree. So again, it is a binary search tree with self-balancing, and which is developed by the Rudolph Ware, which is also called as symmetric binary bit tree. So here, inside the red-black tree, we are having the particular node color is either red or black. That's why it is called as red-black tree. So here it is not color addition. That's why we are just taking this particular as a so whatever the white color is treated as a red, and whatever the black box that are treated as a black. So it is having this particular condition. The color of node is either red or black. Okay. Then color of root node is always black. So root is always black. All the leaf nodes are black. So whatever the leaf nodes are also black. Okay. So root is black. Root and leaf node are black. So these are the rules. Every red node has both the children color in black. Okay, so every red node, the red node असेल, so its children must be black. And one more, every simple path from a given node to any of its leaf node has an equal number of black nodes. Okay, so whatever the path which is from root to whatever the leaf node, the root to leaf node path is equal to number of black nodes. Okay, so just check. So for this particular null, the path is 1, 2, 3. So just check whatever the black trees, black nodes, 1, 2, 3. So again for this particular path is 1, 2, 3, 4. So check the particular black trees 1, 2, 3, 4. Okay. So in this way, we have the whatever the number of nodes, and these are the particular rules related to the black tree. So these are the particular examples related to the red black tree. Then just check the operations. So while searching the particular node, again it is exactly same as the binary search tree. So there is no change. We have to just go through the left root node. So if it is less, go to the left part. If it is right, go to the right part, and so on. Okay. Then inserting a node in a black tree. So there are the few conditions to insert the particular node in the black tree. Okay, so these are the particular cases. If new node is root node, so if it is root node, then just paint it with the black. So root node is a black. Okay, so only this particular condition. Second, if both parent and uncle are red. Suppose if new node is coming. Okay, so its parent and this is the uncle. So P and U are in the red color. Then what are the condition? We have to just change the color of the grandparent. So whatever the color of this particular node, we have to just change color. Change the color of uncle and parent. Again, we have to just change the color of uncle and parent. Okay, so whatever the red color, we have to just transfer to the black. Whatever the black color, we have to just transfer to the red. And this is the new node. So these are the particular modifications which you want to do. When the new node is inserted and parent color is red. So in that particular case, we have to just refer this particular change. Okay, so we have to just shift the particular coloring like this. So first of all, grandparent, we have to just change from blue to red, black to red. Then this parent color, we have to just change from red to black after insertion of the particular node color. Then third condition, if parent color is red, but uncle is black, then you have to just, and n is at the right child of p. Okay, so if n means new node. So if new node is inserted at the right, and whether the parent is red and uncle is black. So in that particular scenario, what happened? We have to just interchange the position of the parent and child. Okay, so we have to just exchange this particular position. Okay, so new node is over here and parent node is just over here. So we have to just apply the interchanging of the node. So this is the case when parent is red but uncle is black and new node is at the right side. If it is same condition and if new node is at the left child, so what happen? We have to first, so this is the particular case. So new node at the left side, parent is red and uncle is black. So what to do? In that particular case, first we would rotate clockwise grandparent to the new node. So whatever the grandparent, we have to just rotate. So this is the new position of the grandparent. Then exchange the color of grandparent with parent of new node. So what is the color of this particular parent? So color of grandparent is black and color of the parent is red. So we have to exchange. So here parent color is black and grandparent is red, and keep uncle color as it is. Okay, so these are the particular conditions for inserting the particular node. So if new node, then just apply it as black color. If uncle and parent both are red, so in that particular case, you have to just apply this particular color exchange. If right side, if left side and both colors are different, then apply this particular case. So let's see the example. Consider the red black tree given and insert the 14. So where to insert the 14? The 14 must be insert at this particular location. So here which condition we have to fulfill? That is if both parent and uncle are red. So this particular condition we have to just fulfill. So here parent and uncle color is red. So we have to just interchange the particular color. So 14. So black, black, and grandparent we have to just change as a red. Okay, so this is the case 2. Refer case 2. Now node is 16. It has red parent and uncle is black. Okay, so we have to just apply this particular. So write subtree. So apply the case number. Three. case 3. Okay, so for this particular node. Then we have to just rotate this particular, and again now red parent is red, uncle is black. The new node is this particular 13. So now we have to again left shift. So case number 4 we have to apply, and we have to rotate as like this. So in this way, in each example, we have to just apply the multiple cases, and we can just apply the left, right shift and so on. So you can able to just construct the particular tree. Okay, so insert the particular nodes 64, 89 and 90 in the given tree. So in that particular case, you can just apply this particular operations. So once you just go through this, you can definitely find the particular content. The next one, that is last operation, that is the deletion of the particular node. That is how to delete the particular nodes. So first case, that is if it is root, then you directly remove the particular element and just delete each and everything. So we have to just delete the whole node. Again, so here we have to just use the first case, that is if either node is deleted or its child is read. Okay, so if sibling is yes, is read. Okay, so whatever the sibling means what? Whatever the node which is at the right or left, and it is in read format. So in this particular case, interchange the P and S colors, rotate left at P, and S become the new grandparent. So we have to just apply the rotation. So this particular node becomes the over here. This particular node goes to here, and this particular node goes to here, and this node we have to just delete it. Deleted node. This node. Now suppose if parent, so these are the again next cases. P, S and S children are black. That is parent, sibling, as well as the sibling children are black. So in that particular case, you can just apply this particular case. If sibling and siblings parents are sibling children are black, but parent is red, so you just apply this particular case. Then left child of P and sibling is black, and sibling left child is red, and sibling right child is black. So in that particular case, you can apply this particular fifth case. If sibling is black, if sibling right child is red, if left child of its parent is node. So in that particular case, you can apply the 6 number case. Okay. So all these particular cases that are explained over here with examples. So you can just go through that particular examples. So there are a number of cases related to that particular siblings and childs. So all these particular examples are explained and they are just given this particular. So you can just work out on these particular examples so that you can just go through this particular red black tree. Okay, so again, so these are the particular contents related to the red black tree. Okay, so all these particular things which are related to the optimal binary search tree. So once again, you can just go through that particular contents so that you can get to know what are the particular facts related to the each and everything